Okay, so in this video, we're going to be going over a Euclidean question that has a lot to do with the prop theorem, a triangle that is divided proportionally by parallel lines. Let's get into it. 9.1. Complete the following statement: a line drawn parallel to one side of a triangle. Hopefully, you remember this theorem. This is our prop theorem. It has to do with our prop theorem. What does our prop theorem tell us? Well, first and foremost, when it comes to our prop theorem, we have to just imagine a triangle. Now, within this triangle, you have a line that is parallel to one side of the triangle. Okay, it is parallel to one side of the triangle, and it is also usually parallel to the base of that triangle. So what happens is this line over here that is parallel to the one side of the triangle divides the entire triangle proportionally. Okay, so let's say, for instance, we've labeled this as A, B, C, D, E. So since we have a line that is parallel to one side of the triangle, this parallel line divides it proportionately, right? So that means that line AB over line BC is going to be equal to line AD over DE. Okay, so it divided the triangle in proportion. That is exactly what the prop theorem tells us. So if we want to complete the statement, it tells us a line drawn parallel to one side of a triangle divides the other two sides proportionally. Okay, just like I've explained. Okay, let's look at 9.2. In the figure, we have KL that is parallel to QR. We just want to highlight that. They told us that KL is parallel to QR, so we're just going to highlight that in the same color. And they tell us that KN is parallel to PR, so we're just going to highlight that in the same color as well. KN is parallel to PR. We're going to highlight that in the same color. Then they tell us that LM is parallel to PQ. So we're going to highlight that in the exact same color as well. Okay, so we're also just going to go back and label the units on the diagram. So PK equals to 3 units. I'm going to label that as 3. PL equals to 4 units. I'm going to label that as 4. LR equals to 6 units. And then MN equals to 1.8 units. So we have to calculate the length of KQ. What do we do? Before we begin, let's go back and analyze what is happening with the different parallel lines that are within this triangle. Let's first start off with KL is parallel to QR. Now, we first want to check to see if the prop theorem actually applies over here. We have KL that divides the triangle, or that's parallel to one side of the triangle, and it so happens to be parallel to the bottom, to the base of this triangle. So it definitely divides this triangle in proportion, making that, and it ensures that PK over KQ equals to PL over LR. Let's look at the blue lines. We have PQ that is parallel to LM. The prop theorem also applies over here. Just readjust the way you view these triangles, guys. You need to start looking at it from different angles. Don't just look at it from the way, it's visibly, just from the way it is, drawn right in front of you. One thing about Euclidean, you need to shift your perspective, your viewpoints. Try and adjust your screen. Try and adjust your page. So we have LM that's a parallel to PQ. What does that mean? That means it divides this triangle in proportion, making sure that LR over LP is equal to MR over QM. Now let's look at the final lines that are parallel to each other. KN, which is parallel to PR, same thing. You need to, because there are many different triangles within this triangle. If you look at it from this side, there's triangle QPR. From this side, PQR. If you're looking at the blue lines, then you're going to see it as RQP. You need to look at the different triangles, right? So KN is parallel to PR. It divides triangle QRP in proportion, making sure that QK over PQ is in proportional. It's equal to QN over NR, right? So we've already went over that. We've touched on that. So now let's continue. So we have to calculate the length of KQ. Remember what KQ is parallel what? So we first have to understand where exactly KQ is. KQ is literally over here. Okay, and KQ is literally right next to the green parallel lines. KL that's parallel to QR. So we can easily use our prop theorem by saying that KP over KQ equals to PL over LS, because guys, remember, you need to start with the part of the triangle that has information, that actually has units. No other part of the triangle has units, has those values. We know that PL equals to 4 units, LR equals 6 units, PK equals 3. It's so easy to calculate what KQ is by using the prop theorem, and we're literally connecting it, we're correlating it to sides that already have values. So what we want to do is we want to say that PQ over KQ equals to PL over LR. We're going to cross multiply and try and find out what that value is. So you're going to say that KQ, since remember KL is, parallel to QR in a divising proportion. So we are going to say that KP, which is 3 over KQ, which is over here, equals to the LR, which is 6 over 4. Cross multiply. And please remember to state what theorem you're using, what theorem you're abiding by. It's the prop theorem, and then you have to state the two lines that are parallel to each other, that reinforces, that allows us to use this prop theorem. It's because KL is parallel to QR. And then you want to cross multiply, giving you an answer of 4.5 units. From 2.2, we have to prove that QM equals 2NR. So we have QM, which is this line over here, and we have to prove that it equals to NR. So we basically have to identify the side that they are both equal to, a side that they both have in common. Now, let's first label or list all the sides that QM is parallel. Let's focus on the parallel lines because we're looking at parallel lines over here. But what you also have to understand is you need to look at the different properties of your quadrilaterals. So we can clearly see that KQML is a parallelogram. Why is that? A few properties of a parallelogram would be the fact that opposite sides are parallel and equal. So we know that KL is parallel to QR. It's parallel, KL is parallel to QR. Please remember that when one side is parallel to even a part of the entire line, it still means that this side is parallel to that side. So for instance, KL is parallel to QR, but KL is also going to be parallel to QM because QM is a part of QR, right? So that's one property that we have ticked off, right? And we know that LM is parallel to PQ. Just like I explained previously, even though LM is specifically parallel to PQ, KQ is a part of PQ. So that means LM is going to be parallel to KQ. So now we've already proved that opposite sides of a parallelogram are equal to or parallel to each other. Remember, two pairs of opposite sides of a parallelogram have to be parallel to each other in order for it to be a parallelogram, okay? So we know that LM is parallel to KQ and KL is equal to QM. So what does that mean? That means opposite sides are equal to each other. We've already proved that it's a parallelogram. So now we can easily say that KL for that reason is equal to QM because we've already, identified the fact, we've already confirmed the fact that it is an actual parallelogram. So now we know that KL is going to equal to QM. We need to somehow relate or connect QM to NR. So let's pay attention to which parallelogram NR is a part of. NR is a part of KNRL. That is the parallelogram it's a part of. Now, LR is parallel to KN, and KL is parallel to QR. But just like with what I said previously, since KL is parallel to QR, since NR is a part of the QR line, that means KL will also be parallel to NR since NR is a part of the QR line anyway. So KL is parallel to NR, and just like I've said now, LR is parallel to KN, and that just with that we've already proved that it's a parallelogram, right? Now that we've proved it's a parallelogram, we can immediately start labeling the properties, annotating those properties onto this parallelogram, right? So we definitely already know that KL for that reason is going to equal to NR, and KN is going to equal to LR because one of the properties tells us that opposite sides of a parallelogram are equal to each other. So now that we know KL also equals to NR, but KL was also equal to QM, now we finally prove that those two lines are equal to each other. So what you want to say is you first want to say that KL, right over here, KL equals to QM, and you have to state the fact that opposite sides of a parallelogram, you have to state the parallelogram QKLM are equal. Then you have to, and just like I proved previously, we already proved that KL is also equal to NR, right? Because the opposite sides of the parallelogram, NKLR are equal. So that means NR is equal to KL. Okay, so with that being said, you have to state the fact that KL equals to QM. KL equals to QM, and just like I've showed you previously, KL equals to NR because we've proved and we've identified the fact that those are quadrilaterals. They so happen to be parallelograms. Okay, so since KL is equal to both QM and NR, that means that QM and NR are going to be equal to each other because they're both equal to KL, and that's going to be a reason. Okay, so we're done with this video. In the next video, we're going to be going over some more questions very similar to this one.